Hello, this is Advent of Code, day number 13 in 2021. We are just about halfway through the year of Advent of Code, which is exciting. Definitely after today's puzzle is complete. I'll say after I get 1 star today, the number of stars will be half earned, which will be nice. But obviously the more challenging puzzles come at the end, so we are far from done with the interesting algorithms learning and stuff. Awesome. Well, let's go ahead and dive in. So yesterday I did a little bit of work off stream because while I did get some traces yesterday, I admit I was not wholly satisfied with the state of optimization. I was seeing it take, anywhere between 3 to 5 seconds, let's say, and I knew I could get it faster. So what I did off stream was I went ahead and I parallelized this with Go routines, which happens to run faster in my machine, and I suspect the reason is this, which is I have 16 cores. And because I have 16 cores, it turns out that I can be a lot quicker if I am utilizing all of them, because each individual core is actually not that fast. Right, so if I actually show you my hardware info, it turns out that these cores are Cortex A72 at 2.2 gigahertz, which is not terribly fast, especially given that the IPC is not that great on the older generation of ARM processors. So yeah, it turns out that going wide is better than going narrow. So basically, what I did afterwards was I went ahead and used the weight group pattern and stood up a bunch of Go routines, one for every item in the queue, and just ran them down until they all finished, and then I collected them to get the results. So that turned out to run about 2 to 3 times faster, at least on my setup, which was good to see. The other interesting thing that I did there was I realized that I was spending a lot of time repeatedly iterating over the list of already visited nodes, and that I wasn't necessarily I could do a linear time access instead to just find out whether I'd visited the node before. Granted, it is a little bit more inefficient to copy the map over as opposed to just doing the in-memory copy of the list. And a coworker actually showed me something interesting, which is if you do a depth first rather than a breadth first search here, what winds up happening is you are able to, down here, where we did this work to copy, right, where we did the path.extend, you don't actually need to copy it because every single child that you have is extending your existing slice and just permitting the last element. And then when you return, you can just pop off that element and continue reusing the same slice that you're growing and shrinking, but you're not copying every element in the slice every time. Whereas what I was doing over here was I was actually having to recopy the slice over and over again for every item I was putting on the work queue, because there was no guarantee that items that were related in the work queue were going to turn up in the same place and get to reuse the same reuse the same memory. So his solution runs about 5 times faster than mine, at least on his hardware. And what was interesting was I started taking some of the ideas I had about how to optimize this a little bit more for a thing that might work better for someone with a faster CPU. And what turns out to be the case is every single attempt that I made to optimize it, let's actually zoom in on this part here. You can actually see this, right? Like I did a bunch of runs that were taking like somewhere between 4 and 10 seconds to run, even without OBS running. And when I just reverted the code, it went back to reliably running at about 1.2 seconds. So yeah, I think it turns out to be actually counterproductive. It turns out to be counterproductive to try to play fiddly games. It turns out you can get results in under a second if you just do things. If you just do things in parallel with a moderate degree of efficiency. So yeah. So if you tuned in the stream last time, feel free to check out the changes that I've made since then. I'll drop a link into the chat. But that was yesterday's puzzle, and as we all know, the puzzles just keep marching on and on. So we have a new puzzle that's unlocking in 3 minutes, and I look forward to solving it with all of you. So I've gone ahead and set up the scaffolding, and this time the scaffolding actually has all of the stuff required to trace with OpenTelemetry, because we figured out, for instance, on the stream last time that you have to actually shut down the trace provider. You cannot just shut down the exporter. If you shut down the exporter without shutting down the trace provider, what happens is you kill the process, and the trace spans that are being buffered are not sent to the exporter, or they're sent to an exporter that is shut down, and those trace spans don't go anywhere. So, yeah. It is nice finally having the ability to introspect my code and to see, you know, how long am I taking inside of each section. Let's drop the service name. The service name is not useful here, right? Like, to be able to see, this is how long it takes with good and efficient parallelism to run across something like tens of thousands of searches in each iteration. The other interesting thing that, by the way, this tells me is that a depth-first search actually will succeed in a reasonably finite amount of time. I worry a lot in terms of doing stack overflows when I do depth any kind of recursion. But here, this shows me that even if I were to recurse, the longest path length that I could get would be something like 1, 2, 3, 4, 5, right? Like, you know what? Actually, this would be faster. Yeah, there are 17 of these iterations, so at most the stack depth would be 17, which is not the end of the world. Hi Viwu. Yeah, let's go. Let's do this. The other cool thing that I can show here is I can show stats, right? So I can show queue length. I can also show the paths so far, right, and show you how it progresses as you go along. So you can see towards the end, there are not very many elements in the work queue, but in the middle, there's like a lot of stuff in the work queue, and a lot of it is panning out and actually reaching the end. Hi, Dunya. Nice to meet you. Cool. So, yeah, I am now doing tracing on Advent of Code, so I'll just keep this open just in case it winds up being helpful or useful to me to have a tracing capability in here. And yeah, that is what I have going on today. All right, let's tab back over. We've got about a minute until we get started. Let's go ahead and get a file open to hold my input. And thank you. Good luck to you too. All right. Let's take a look at this. It's a weeknight puzzle. I'm guessing it will be like a step up over last week's weeknight puzzles, but most people are still not on paid time off, so I'm going to guess that this one will be a little bit, maybe about the same as days 10 or 12, but probably not going to be dramatically harder. We'll see. Of course, harder depends on each person, right? Like what you know and what you don't know can vary a lot. So. Feeling pretty ready for this, although I didn't fill my water mug before this, but oh well, that happens. It'll be all right, I'm sure. All right, 3, 2, 1, and let's go. Oh, okay. So we've got coordinates and instructions of where you're supposed to fold. Some of the dots might end up overlapping. Okay. If they overlap, they merge and become a single dot. Yep. Okay, so this is just going to, this is just a gut check just to make sure that your fold is correct. And after it checks that your fold algorithm is correct, then it'll get to the harder stuff. Great. Okay. So let's do this. So let's go ahead and gotta move my mic out of the way. There we go. All right, so we have a bunch of x, y coordinates. Okay, we sometimes do here, so this is just going to be our standard code for doing something like this. And we can ignore the error. That should be a Y. All right, and do our standard thing here as well. Yeah, okay, that'll be fine. So the paper is going to have a map of chord to bool. Okay, wonderful. All right. If S is the blank string, then parsing coordinates equals false, and we continue. Else, we're going to get something that looks like this. It's going to say fold along, and then it'll give me a line. So it'll look something like this. Okay. And we need the offset, which is going to be an int. Okay. So we're going to make a paper, and then paper chord xy is true. And we also need folds. Going to be make of fold, although as we discussed in the last stream, it would be better to just express this like that. Okay, so this is going to be, you know what, that's fine. I can just hard code this. I don't really care about the efficiency of parsing the input, and that saves me from manually checking it. So S index length of fold long. So it's going to produce for me then fold all right. Okay, fold dot x-axis true. And then, finally, we're going to take offset, circond a to I of S from index the trick. Okay. Now, let's just make sure that we have all these things correct. Oh, and the other thing I need is folds equals append, folds, fold. Okay. It's going to complain that I have unused, it's going to complain that I have unused variables, and that's fine. Yep, there we go. 19, oh, struct. Okay, we're going to end comment. We're going to comment these for now. Line 24, oh, struct as well, there. All right. And, oh, no, I do use OTel. Okay, that's fine. Oh, and I need context. All right. Cool. So let's check that this matches my input. So y equals 6. We are also supposed to fold along x 655. Okay, that looks good. Okay. Great. So the other thing to check is, do all of these look reasonable? For instance, I should see somewhere in here a reference to 1309 334. Yep. I see a reference to... Interesting. Did they introduce sorting of maps when they were displayed for printing these days? That's kind of cool. 189, 281, 189. I did not know that they'd implemented deterministic printing of map orders. I know when you iterate, you don't necessarily get a predictable order. 189, 281. Yep. Okay, so I have the correct list of folds. I have the correct list of coordinates. That is a wonderful thing to check. Okay, so now that we have done that, so we're just going to iterate this the first time. We're going to do something like this for now, and we'll fix that up later when we have a part B. Okay, and finally, new paper equals, or paper equals new paper. Okay, so we're going to iterate over our old paper, and depending upon whether it's a x-axis fold or not, that'll determine what we do. If f dot offset is greater than f less than, else this should never happen. We should never fold on it. Fold the bottom half up. So basically this is always making the paper smaller. So if we're folding along the x-axis, if it's greater than, we need to mirror it. Its current position. Oh, wait, that's wrong. So Okay, so that's pretty straightforward. We also need a paper, new paper, make paper. All right, so this one is the easy case. So that's a printf. Yep, that's fine. Although that could equally all be f offset. Let's do that way for simplicity. Okay. So how do we handle the mirroring? New paper. So the y offset, or wait. If I'm folding on the x, then it's the y that is changing. Okay. Wait. No, the horizontal lines have the consistent y. Okay, I had it right the first time. Okay. So this is folding. Oh, I just had the word left. Left over the offset line. So diff is going to be chord x minus f offset. So the y winds up being the same, but chord f offset minus diff. Okay, that seems to be clean enough. And otherwise, we do this, except for slightly different. And yes, I could do this with pointers, but for now, I'm going to leave it like this in case they throw us a curveball. Up, over, so this is y, x, offset minus diff, chord y, and this is y. Okay, so if it's less, we leave it. If it's greater than, we fold it up, keeping the x coordinate. But if it's one below, it goes one above, etc., etc. Okay. So oh, and this needs to be a colon equals. All right, let's go ahead and run it, see what happens. 795. That's correct. Okay, part 2. The manual says the code is always 8 capital letters. Okay, so now we run it to completion. Okay, so now we need to gather min max x 0 var max x max y if chords x is greater than max x. Well, okay, so I have tidying to do. That is all good. I am not going to set a speed record because I was, enjoying doing this and chatting with you all, and that's fine. This should be max y. Okay, so now we get to actually do the iteration. 4 0 x is greater less than or equal to max x plus up, and this should also get encased in a y first. Okay. If paper cord xy printf hash, otherwise printf dot, and okay, that should do the trick. Oh, this is just over range paper. Okay, so this seems to read CEJKLUGJ. That's correct, rank 704, very nice. How did I get in the top 1,000? Like, I feel like I was going pretty slowly there, but okay. I will accept that. Yeah, I'm not going to do any image recognition. This is fine. I am perfectly happy to have done it this way. Okay, so cleanup time. I think the primary thing that I should do is I should write a function that performs the fold operation. So we're just going to do it this way. Actually, before I do this, let's actually just add this to my get working buffer. Yeah, this one was really fun. I'm a fan. Okay, so yeah, I don't think I really want to be using honeycomb trace here. I mean, I could, but there's like there's nothing interesting to show here, I think. So we're going to just snarfle all of this. And we'll think about how to do this. Okay, so yeah, I don't know how someone could have gotten tripped up on this, but I assume we'll find out when we start rating people and find out. Parts 1 and 2, very funny, y'all. Very funny, y'all. Okay, I think that's fine now, and then so in here, what we're going to do is var dimension int if x axis, then yeah, no, this has to be per thing. So if x-axis diff is going to be chord x minus f offset, else diff equals chord y minus f offset. So now, we don't need this. So if diff is greater than 0, else if diff is less than 0. So here, f, okay. So new chord is chord to start with. Then new chord how do I do this? So if I'm folding over the x-axis, would someone in my chat like to answer what advent of code is while I work on this? In short, advent of code is a set of coding puzzles that you can do. New chord x equals f is diff. Else chord y and new chord. Actually, it's okay to modify chord in place. That's okay. That's safe to do. Okay, so let's try running that. And let's just watch it go. Oh, I didn't define paper. That's fine. Yep, still get the same answer. That all looks fine to me. Great. Anything else I need to comment before I do this? I don't think so. Yeah, I think this is all reasonably self-explanatory here. So I'm going to go ahead and commit this then. And we did not use tracing this time, so I'm going to get rid of all of the references to tracing in context here. If I need them, they're going to be there for me, but I did not need them this time. All right, make sure one more time that it still compiles and runs. There we go. All right. All right. Oh, and I don't want to commit this swap file. All right, let's make sure my commit's clean. Good. Day 13 solution. All right, let's go ahead and push that up to the cloud, where you can all have a look at it. This is going to be over here on my GitHub. And thank you very much for all tuning in. And we will get to I'm catching up to scroll back now. Yeah, day 20 yesterday was hilarious, or day 20 last year was hilarious. The way that I solved the sea monster puzzle last year was that I looked around at the number of dots that were potentially going to be part of sea monsters, and then I took a guess based off of the density of sea monsters that I thought could be present. So I think that there were like 20 sea monsters. And I knew that each sea monster had, I think, like 15 or 20 or however many characters in it that would be eliminated from consideration once you got rid of the sea monster in order to just get the remaining waves. So I subtracted the number of sea monsters times the pixels per sea monster from the total number of waves. So even though my pattern matching to find sea monsters was not working correctly, I was still able to, or it wasn't even that my pattern matching to find sea monsters was not working correctly. I was not able to unscramble it. However, I did know that all of the borders of every tile would go away. So I knew exactly how many choppy wave tiles there were going to be inside of the image, even if I didn't know which way they were rotated, to be able to figure out where the sea monsters were. So that's how I kind of magically solved day 20 last year the wrong way. And then I went back and solved it, of course, on stream. But that was at the end of a couple of hours of like bashing my head into having the wrong data construct. But cool. All right, let's go ahead and raid someone else. And for everyone else, I will, for everyone who's not coming along for the journey, I'll see you tomorrow about the same time. Cheers. Let's go ahead and raid. Where is X?